Good morning, good afternoon, or good evening, depending on wherever you are. And thank you for joining us for our first AMETEK Solid-State Controls webinar of 2022. It's been a few months since I've done a webinar, so thank you for joining me. I know you have very busy lives and schedules, and I really do appreciate you taking the time out of your day to come and watch this. So we'll just wait for everybody to join, and if you could type in the comment bars, as always, if you can hear me okay. That's the first check that I always like to do. So please do use the chat bar and let me know if you can hear me okay. And I'll wait to see if everyone can hear me. Cool. Taylor's let me know that she can hear me. So that is a good thing. Don't want to speak to myself all day. My name's Craig Williams. I'm the Senior Technical Manager for AMETEK Solid-State Controls. And I'm based in the Stafford office here in Houston, Texas. I have 20 years, actually over 20 years now in the industrial UPS industry, and I've worked with all of the major UPS charger manufacturers that are out there. So I'd like to think that I have a little bit of experience and know what I'm talking about, a little bit anyway. There will be a lag of around 30 seconds between you hearing my voice and me seeing a question. Basically, Webinar Jam has to transmit this webinar out on Windows-based devices, iOS-based devices, and Android-based devices. So there is some processing and conversion that needs to be done. So from when I speak, it takes about 15 to 30 seconds for you to hear me. So when I say something and then you post something in the chat bar, there is going to be a little bit of a delay. And for that reason, we usually wait until the very end to answer any questions. So I will go through all the questions at the end. If I do see a question while I'm going through the presentation and it's pertinent to what I'm talking about, then I'll try and pick it up there and then. But understand, if you do type something and I don't answer it straight away, it's probably because I'm going to leave it till the end. Webinar Jam has a panic button. What that means is if there is any connection issues, then what I can do is press the panic button, and that creates a whole new room, invites everybody to the new webinar room, and we just continue from where we left off. A very common question is, will the webinar be recorded? And the answer to that is yes. If you registered for the webinar, you will get a link within an hour or so to rewatch the webinar through the Webinar Jam platform. That recording is not fast forward, rewind. You know, you have to play it from the start and watch it all the way through, just like you were watching the webinar all over again. But what Taylor and our fantastic marketing team do is they will download that recording to an MP4, and then we'll upload it back to the AMETEK Solid-State Controls website, our YouTube website, and we will share that link to everybody that was on this webinar. Somebody's asked a question already. Are we currently muted? Yes, everybody is muted while I do this webinar. You can just type in your questions in the chat bar and I'll see them that way. That way we won't get too many people speaking and interacting at the same time. And the webinar should last around 1 hour. I'm historically terrible at sticking to that time frame. I usually run over, but I'm going to try my best as always. But I really do like talking about UPS systems, so I may get sidetracked here, there, and everywhere. So apologies in advance if it does go a little bit too far. But we do have a question and answer session at the end as well, and that usually drags us over the timeline. But if you want to hang out and stay for over the hour, then I am good with that. Okay, so everybody seems to be here, and they've replied that they can hear me. So let's get started. So what we're trying to get out of today's webinar, the objectives, we want to understand the major UPS topologies, understand the blocks inside different UPS systems, discuss the advantages and disadvantages of each of the topologies, and then discuss the power flow and general operation of each topology. And when I say topology, I just mean how the system is set up, whether it's parallel, single, cascade, things like that. And we'll get to that in a little while. Okay. So the first thing we're going to go over is components that make up an AC UPS. And when I say an AC UPS, I mean a UPS that has an AC output rather than a DC output. So first of all, you have your normal source AC input, which is also called the primary supply, or if you're in Europe, it's called the main supply. But that is usually, for most industrial systems, it's a three-phase 480 volt input to the UPS. Then that goes into the battery charger or rectifier, which converts that normal source AC into DC, which charges the batteries. The batteries are there to provide backup power during loss of the normal source power. And then the inverter converts the DC back to AC and provides power to the load. And then we also have, and there's a little bit of confusion about this, what's called the bypass source. It can be called the bypass, the auxiliary power source, or even the reserve supply. All the terms are interchangeable, and that is unregulated, usually unregulated power that comes directly from an MCC. It has no inverter behind it. It's just raw power from the grid. Then we also have a static transfer switch, and that is an automatic switch that connects the load to the inverter or the load to the bypass. And it's a switch that has no moving parts, which is why it's called a static transfer switch, static as in no moving parts. And it uses SCRs, which are silicon control rectifiers, to perform that function. And then the last thing that we're going to discuss is the remote bypass switch, which is a make before break mechanical switch that removes power from the UPS cabinet to allow safe maintenance. And it's a physical switch, or in some circumstances, it could be a breaker arrangement. Okay. So what I first want to go over is what we class as a commercial UPS. And because I want to show the differences between a commercial UPS and an industrial UPS, because that's a very common question. So you can see on the screen here, and what I'll do, so this, sorry, let me just draw that circle again. I'm terrible at drawing with this pen. This is actually the UPS module, this box here, okay? And then all these boxes here, here, and here are external to this UPS. And for a usual commercial UPS, you will have a 480 volt AC input. You will have a high DC battery usually on a commercial UPS. Usually it's a 480 volt battery, which is 240 cells lead acid. And the output is usually 480 volts, three-phase on a commercial UPS. And therefore, that means that the bypass has to be 480 volt three-phase as well, because the bypass must match the output of the UPS. And what a lot of people get confused about, especially with a commercial UPS, is yes, we do have a high DC battery. It's at 480 volts. But the DC bus between the charger and the inverter actually gets boosted up, and it can be as high as 650 volts DC. Okay. They use high voltages inside commercial UPSs usually. And there's a good reason for that. And that is because the higher the voltage, the lower the current. So if you're going to buy components or wiring for inside a UPS, if you can save money by increasing the voltage, which therefore reduces the current. You can use less copper. You can use lower rated IGBTs and SCRs inside your system, and it just makes it easier to build a cheaper system. So that is why most commercial UPSs use a high DC bus. And the other thing to notice here is that there is a converter in the charger. Not only are we converting AC into DC through this way here, if we do go on battery operation, which I'll show in the next slide, the battery still has to flow through an electronic device to get to the inverter. And we'll get to that in just a moment. Okay. And the other thing to notice inside most commercial UPSs is they have circuit breakers and contactors for a lot of their switching. So you can see here, they have a circuit breaker here, but on the output of the system, rather than have a static switch, they have a contactor. So they don't have an inverter static switch. They do have a bypass static switch, but that bypass static switch is only there for instantaneous switching from inverter to bypass or bypass to inverter. Once that initial switching has been done, this contactor here pulls in and basically bypasses the static switch. We'll explain that over the next slide as well. Now, if you have any knowledge of plant operations, you will know that contactors, although they're fantastic, they aren't the most reliable of things because they're mechanical. They have electromechanical coils, and they also, it moves, and things can get stuck. Coils can burn out, and these can fail. So you can see this is in the critical path to the output of the system. And if that contactor fails in the open position, gets stuck in the open position, then you cannot supply power from the inverter to the load circuits. So in my opinion, it's not great having a contactor as the output on the critical path of the inverter to the load. That's my opinion. And the other thing to notice about commercial UPS, and once again, one of the reasons why they are usually smaller and cheaper, is there is no isolation transformer on the input or on the output. And that's quite important, especially to stop faults propagating back onto other supplies. So for example, let's say you have a battery going in here and you have a failure in this charger section, which is a short circuit. And that allows DC to feed all the way back to the MCC. And obviously, DC getting pushed back onto your MCC is a bad thing because there are many other loads connected to the MCC that can't tolerate a DC being reflected back. Now, in truth, in this commercial UPS, there will be some form of protection to monitor if there is a short in this charger. And then maybe what it will do is trip this breaker here to prevent that DC getting back. But once again, you're relying on circuitry to do that for you. If you had an isolation transformer here, it's as simple as DC can't flow back that way. The transformer stops it, and there is no way DC can propagate back onto this MCC here. Okay. All industrial UPSs will have an AC input isolation transformer. And the same can be said for a transformer here. If you had a fault in here and DC shorted through this way, without a transformer, that DC could propagate onto the output circuits and cause damage or issues. But with a transformer there, it can't, the DC will not flow through a transformer, and it prevents the DC propagating onto the output if there's a fault. So here is the standard operation of a commercial UPS. Okay, in normal operation, the red is the power flow. You can see it, his key here, and the green is energized and ready. So in normal operation, power flows from the AC input into the charger, converter. Okay, in a commercial UPS, it takes that 480 volts and it just directly, using a diode rectifier bridge, not a control bridge, it rectifies that 480 volts into round about 650 volts DC. Okay, so you're going to have 650 volts feeding the inverter DC, and that DC gets turned into AC, which is at 480 volts, and then it flows out this way to your output circuits. And then what the converter does here is it converts that 650 volts down to the correct charge voltage for the external battery. It's a 480 volts nominal, so it's going to be probably around about 530 volts DC for the float charge level. I can't remember the calculation. It's 2.25 times 240. And that keeps the batteries charged. Bypass is available, and it goes all the way to this contactor here. Contactor is open. I know it's drawn closed, but this is a PDF drawing that was taken from a manufacturer's website. And then CB3 is closed. So the power from the bypass does get to this static switch here, but this static switch is off at the moment, okay? And doesn't allow power to flow through. Power flows through to the output from the inverter and keeps critical loads powered. And then if we have a power failure, then we go on to battery. And you can see the battery is now coming up here. Once again, it's a 480 volt nominal system, but it does go through this electronic DC to DC converter, and it converts the 480 volts up to around about 650 volts. So there is conversion happening there. There is electronic circuitry required to get that 480 volts to 650 volts. But then the other operation is as if nothing has happened. The inverter still goes, carries on regardless, and the contactor here is closed. And then if that battery depletes all the way down to its low voltage level, then the UPS is going to switch over to bypass. It says, okay, my battery is getting too low now. We have to do something about it. And what it does is it switches off the inverter. It will probably trip this battery breaker here. And before it does all of that, it will transfer the system using this static transfer switch here immediately to the bypass supply. You will be on bypass supply once the battery has depleted. And then the last thing that the commercial UPS does in that circumstance is once the initial transfer has taken place using the static transfer switch, it will then close this contactor here, and it will bypass the SCRs in the static switch, and the bypass will feed all the way through this line here. So the static switch in a commercial UPS is usually only rated for a very short period of time to allow the initial transfer to take place, and then this contactor here takes over. Okay. So that was a commercial UPS. And I'm not going to badmouth commercial UPSs. They do have their upsides and they do have their downsides. But I'm not here to criticize them. I'm here to show you the difference between a commercial UPS and an industrial UPS. And this is the double conversion industrial UPS. And obviously, we're AMETEK solid state controls. So this is an AMETEK solid state controls diagram. And you can see here, usually our output, very similar to the commercial UPS, we use 480 volt three phase on the AC input. But what differs from us and the commercial UPS is we tend to use 120 volts AC output and bypass supply. And we'll explain that in a few slides along. And you can see here, we do have the isolation transformers to prevent faults propagating either onto the loads or back onto the MCC. And our batteries are usually 60-cell lead acid batteries at 120 volts, but we do have some customers who want 240 volt DC batteries. It just depends on the UPS that's being replaced and the backup time that you require. But most systems that we design do have 120 volt nominal battery. And once again, I'm going to walk through the power flow for an industrial UPS. So in normal operation, 480 volts AC comes in, goes through the transformer, gets stepped down to a voltage within the system that is acceptable for the battery charger rectifier, and then that converts the AC into DC. And in this circumstance here, we have a 60 cell battery. So that means our float voltage is going to be 135 volts DC. Okay. So the batteries are kept charged by the charger, but the charger also supplies the current into the inverter. And we don't do any conversion. Remember on the last commercial UPS, this was boosted up to 650 volts. Here we stay at 135 volts into the inverter. And that DC gets changed back into AC. And that goes through a transformer, which makes sure that the output here is 120 volts. And then rather than go through a contactor, we go through a purpose-built static switch, which is rated for 200% of the load of the system. So it can quite safely handle all the power requirements for the load circuits. And then that goes out to our loads, sometimes through a manual bypass switch or sometimes through a remote manual bypass switch. And just like the commercial UPS, we do have our bypass available. It's ready to go. It's energized. It's 120 volts coming in, and it goes to this static switch, but this static switch is off because this static switch is on, and it's just waiting to be told to turn on if there's an issue with this inverter here. So no power flows from the bypass into the load circuits in normal operation. Very similar to the commercial UPS. If the AC input fails, the battery just continues supplying power to the inverter. And in truth, there is no switching involved here. It's just like you pulling the plug out the side of your laptop. Your laptop carries on going regardless. There's no switching. It doesn't switch to battery. The battery is in parallel with the charger. So once the charger goes off, the battery is just there. It just carries on going regardless. The inverter does not know that there is a difference in power between what's coming from the charger and what's coming from the battery. It just carries on regardless as normal. Okay. Once again, we have to protect the batteries from going below a certain voltage that could irreparably damage those batteries. And for a 60 cell system, that's usually 105 volts DC, which is, if you do the calculation, 1.75 volts per cell times 60. Okay. So if the battery gets to 105 volts DC, what our system does is it says, okay, immediately turn the bypass static switch on. It then turns the inverter static switch off, and then it trips this battery breaker to prevent the batteries discharging anymore. Okay, so now at this point here, you are on bypass through the static switch. Remember the difference between static and manual switch. A manual switch is mechanical. A static switch uses these SCRs. So it's an automatic transfer, seamless, without any issues whatsoever. It was make before break. And that takes care of the loads when the battery is depleted. And then if you want to do any maintenance on the UPS, what you can do is you can move the manual bypass switch to the bypass position, and that takes the power around the static switch down through this bypass switch here and out to the loads. You can open this breaker, open this breaker, and open this breaker, and then all these components here are de-energized and you can work on them. So that was a commercial UPS versus an industrial UPS. Now I want to talk about the different ways that you can connect UPSs. Obviously, you can have a single UPS like we just showed you in the slides before. But the other thing that you can do is you can have a parallel redundant UPS. And that means you connect two UPSs together on the load, on the output of the system, and connect them in parallel. So that's what this drawing shows you here. And it's the same as always. The red is showing you power flow. So a normal operation, we'll call this UPS B and UPS A. In normal operation, both UPSs should be sharing the load. So let's say the load is 10 kVA. Then this UPS will supply 5 kVA, and this UPS will supply 5 kVA. Okay. The bypass supply is still there, ready to go if necessary, but this static switch is off. It's waiting to be turned on in case there is an issue with both of the UPSs. But that is normal operation for a parallel redundant system. And now, if the AC input, the primary AC supply fails for UPS B, then what happens is UPS B will go onto battery. This is specific to an AMETEK SCI parallel redundant system. Some of the other manufacturers, they might handle it slightly differently. But what we do is the UPS B will go onto battery. The inverter will carry on going as normal. And once again, this one here will supply 5 kVA, and this one here will supply 5 kVA if we use the same rating as we did before. Okay. And then if this battery gets down to that 105 volt level, then what we do is we tell this static switch to turn off. We'll trip this breaker here, the inverter will turn off. And then what we say is, rather than transfer to bypass on this UPS, and I'll explain why we can't do that later, we turn this UPS off. So this is no longer supplying that 5 kVA, okay? So now this UPS, UPS A, will now supply the full 10 kVA to the load circuits. Bypass is still there if needed, but UPS A is taking care of the full load. And this will all be done without any disruption to your load circuits whatsoever. Obviously, you will get some alarms on UPS B. It will give you some alarms, but UPS A will carry on going regardless. So that's the basics of a parallel UPS and how it works in normal operation. Actually, let's go through this last slide here before we go into Cascade. The last thing is, if you want to perform maintenance, or if both inverters fail on a parallel system, then what happens is the bypass supply is called into action. The bypass static switch does turn on, and we supply the load circuits. Okay, that static switch is off, that static switch is off. And in truth, in this position here, you can go open these AC breakers, open these DC breakers, and you can go and work on the whole system bolt-free if necessary, depending on the design of the maintenance bypass switch. Just getting ahead of myself there. The other way that you can connect two UPSs together, one of the other ways you can connect two UPSs together, is when you have dual redundancy at the load. Okay, so you can see in this diagram here, it's a little bit messy, but we still have a UPS A and we have a UPS B, but they are not connected in parallel. What happens is each UPS feeds into a power supply, an AC to DC power supply. So this one here is fed from UPS A, and this one here, if you follow it down, is fed from UPS B. And then the power supplies, because it's much easier to parallel DC than it is to parallel AC. So the power supplies here have DC outputs, and they are diode ORed together on the output here. Okay, so really in truth, they're running in parallel with each other. And then usually it's 24 volts DC that comes out of these power supplies, but it could be 48, 12, depending on the system that you bought. And usually, in truth, this is for DCS systems, distributed control systems, where they have the ability to accept usually 3 different AC sources for their DC, for the DCS panel. You can have one fed from the grid, one fed from UPS-A, and one fed from UPS-B, and therefore you have a very robust system, and your DCS will remain powered in most circumstances. Hopefully I explained that okay. And the power flow for this is, once again, if we have a primary AC failure on UPS-B, we just go to battery. Remember, there's no switching. The inverter doesn't care. It's still getting its DC, and it will feed power into the power supplies related to that system. So it's as if nothing happened. You will get an alarm. You'll get an alarm on UPS-B, but the load circuits will see it as if nothing happened. Okay. And then if the battery depletes and gets down to 105 volts and gets taken out of the system, then what happens is this static switch will turn on, and this UPS will go into bypass, because remember, the AC outputs are not connected together. They're not in parallel. So we can have one UPS on inverter and one UPS on bypass at the same time, because the power supplies are giving us the isolation between the 2 outer phase supplies, and therefore it doesn't matter. So all of our power supplies still remain powered in this circumstance. Okay. So I'll go back to that one again. So this is a very robust system, but obviously you need to ensure that all the loads, because this is usually an AC panel, and it will be labeled UPS-A AC panel. And then this one here is UPS-B AC panel. And the only thing that happens when you have a system connected like this is some people will go and they'll attach a load to UPS-A, and they won't replicate that load on UPS-B. And that's when you start to have issues, because if you took this whole system down for maintenance and only relied on this power supply, then if you connected a load to this one, but not to this one down here, then that load will de-energize if you're going to do maintenance on it. So you do have to be careful to replicate all loads when you connect a system like this. And then this topology is called a Cascade UPS. And there's a lot of confusion surrounding a Cascade UPS, but the easiest way to remember it is if you have UPS-A here and UPS-B here, UPS-B is feeding the bypass supply. So this is the bypass static switch for UPS-A. Okay, so really what we're doing is we're putting a UPS onto the bypass supply. So therefore, if something goes wrong with UPS-A, when we transfer to bypass, we still have a UPS backing it up. We still have battery backup. We still have clean power going to your load circuits. So it's actually a very good arrangement. And similarly, actually, when I go back here, if I go back to this slide here, you can have this UPS here could be one manufacturer, and this UPS here could be a different manufacturer when you are paralleling the systems at the loads. Okay. As long as they are rated, this has to be 30 kVA if it's a 30 kVA system, and that has to be 30 kVA. But you could, in theory, I don't know why you would do it, but you can in theory have one manufacturer for that UPS and a different manufacturer for that UPS. And that is the same with a Cascade, because they're not connected in parallel and there's no electronics between the two systems. you could have UPS B could be one manufacturer and UPS A could be a different manufacturer, as long as they are rated the same. So if we lose power on a cascade system, then as always, what happens is the system goes on to battery. Okay, we want to keep these load circuits supplied by an inverter because the inverter gives us clean and regulated AC power out to your load circuits. Okay, we're protecting those load circuits as much as we possibly can. And then if that battery depletes, once again, we turn this static switch on, we turn that static switch off. It's a make before break supply. But in this instance, now what happens is now a UPS that is feeding the bypass for UPS-A. So we still have UPS backup and UPS protection to these loads here. It is still clean and regulated power going to the load circuits in this circumstance. And only when either that battery failed, if we had an AC output there, that battery failed, and both inverters turn off, only then will we go to bypass, which is grid power, and it is now unregulated, and it is not smooth AC. It's whatever the grid is supplying you at the time. Okay. So that's all the different types of topologies you're going to find for UPSs, how they're connected together. There's really only the four main ones: a single UPS, a parallel redundant UPS, a dual UPS using the loads as the parallel connection, and a cascade UPS. Okay, Corey's just asked a question, so I'll go back. He's asked, what happens in a single UPS if we lose primary and bypass supply? So let me go back quickly so I can show you what happens. I can't select the slide using this webinar. Okay, so let me get a better slide where it's got the normal operation. It's this one here. Okay, so what Corey's asking is, if this fails and this fails, what happens is we go on to battery operation. Okay, and the inverter has its own internal clock, is what we call it in the industry, and basically it's set for 60 hertz for the US, 50 hertz for Europe and Asia, and it will run at its own frequency. It's 60 hertz. It will have no reference to the bypass supply, but you won't see any difference in the output. It's just as if we went on battery as normal. So if you lose AC input and bypass at the same time, you'll go onto battery, and your loads will still be protected. So it's a good question. Goodness me, I wish Webinar Jam would allow me to select my slides. It is what it is. Okay, so now we're going to talk about bypass switches, which can get confusing because I think the most common misconception out there is the difference between a static switch and a bypass switch. So we've got a key down here. So we've got our bypass switch. So there's contacts here and there are contacts here, and they are labeled N for normal, BTL for bypass to load, and BI is bypass isolate. And it just so happens that these are what the names that we give to the positions on an AMETEK bypass switch. Okay, some other manufacturers use different labels for their positions. Okay, so in normal operation, you're going to have the static switch is going to be on inverter, but the bypass switch or the manual bypass switch is going to be in the normal position. So these contacts here are connected, And remember, on the bypass, we do have to get power to the static switch, even though it's not on. So those contacts there are connected as well. So there's two sets of contacts inside the manual bypass switch. And in normal operation, they are in the normal position, and that is how it's connected. Now, if we move to the bypass to load position, and the first thing that I'm going to say is always follow the procedure on your UPS, and that procedure will always tell you to first switch from inverter static switch to bypass static switch. So there's usually going to be a push button on the front of your UPS that says bypass to load. Push that push button. This static switch will turn on, and then you move your bypass switch to the bypass to load position. And you can see here that now these two connections are connected. So now the power is flowing around here out to the load circuit. We still have power going to our static switch, and power would flow through here out to here. That allows us to do testing. If we powered the system down, replace some parts, when we power it back up again, we can go to the bypass to load position and test the synchronization between the inverter and the bypass, and put a load bank on the output if we wanted to, and test the inverter. It allows us to do, when I say us, I mean a service engineer from AMETEK Solidstate Controls, to test the system, okay, in the bypass to load position. Then the final position is bypass isolate. And what that does is we move to this top position here, and then we move to this top position here. So now we are stopping power getting from this static switch, so we can no longer test the transfers between inverter and bypass. But what this allows us to do is, if we open this AC input breaker, we open that battery breaker, and because the bypass isolate position, it removes power from here and from here. Everything inside the UPS is now volt free, and we can replace parts safely using NFPA 70 practices. Okay. I do see your question, Kenneth, but I am going to leave it to the end on this occasion. Okay. And then there is a slight difference as well between a manual bypass switch that is connected on the UPS itself to what is called a remote manual bypass switch. And this is specifically, I'm going to discuss an AMETEK Solidstate Controls remote bypass switch. And this portion here is an AMETEK Solidstate Controls bypass switch, and this section here is an AMETEK Solidstate Controls UPS. And the confusing thing that a lot of people get confused about in our systems is, you have to understand, we sell RMBSs, or remote manual bypass switches, as part of a new project. If you buy a UPS from us, we'll recommend that you buy an RMBS. But we do also sell RMBSs separately. So you can, if the person who ordered the UPS maybe 20 years ago didn't buy an RMBS, you can order an RMBS from us and install it at a later date. And it just allows you to work on the UPS safely. And I'll explain that through this diagram. So you can see here that this original UPS has what we call a manual bypass switch on the UPS itself. But that, if, let's say, so we've got 120 volts coming from the bypass. Let's forget about this just now. If we had 120 volts coming in here, if we moved this to bypass position, it would flow through there. Now remember, these terminals are inside the UPS. These terminals are inside the UPS. This breaker, the power will go to here. This breaker is inside the UPS. So yes, we can go and work on this UPS, but we can't do it completely volt free, because inside this UPS, we are going to have live terminals. I hope you understand that. But if you connect an RMBS to your system. When you go to bypass position on the RMBS, it goes, the power flows through here and out here. Then this contact here opens when we're in bypass isolated position. So power does not flow through there. So we are volt free here. And also this is open. So power can't flow through that way there. So these are volt free. So now this is volt free. This is volt free. If we isolate here and here, now the whole system is volt free and we can perform work in there without any issues whatsoever, and do it safely without any arc flash requirements and following NFPA practices. So an RMBS is very convenient when it comes to doing maintenance and if you wanted to replace the UPS. So now I'm going to discuss some common misconceptions that we have about UPSs. And I love this quote from Albert Einstein: anyone who has never made a mistake has never tried anything new. And the reason why I put this slide up here is nobody can be expected to know everything about everything. And nobody can be expected to know everything about UPSs. You're only as good as the person who taught you. And there are things that I got taught 20 years ago when I first started in UPSs that I found out throughout my career were actually incorrect, were wrong. So you're only as good as what you have been taught. So there are a lot of misconceptions out there because some people have been told things that aren't correct. So the first thing I want to discuss is a common misconception is, I must have a 3-phase 208 UPS output. And that's absolute nonsense in most cases, because very, very rarely, I would probably say maybe 1% of the time, is there ever a 208 volt load connected to a UPS. Yes, there is a 208 volt distribution panel connected to most UPSs, but that 208 is then distributed as 120 volts to neutral. All the loads are 120 volts. So it's very, very, very rare that you ever need 208 volts. Okay. And the second line there says they're usually connected to an AC panel where the 120 volts to neutral is applied to a load. And the important thing about this is a 208 UPS will not clear a fault on the output as good as a single phase UPS. Okay. And it's simple engineering math. A 10 kVA 3-phase UPS will only give you 28 amps per phase. Okay. A 10 kVA single phase UPS will give you 83 amps per phase. That's 3.5 times the current. Why is that important? Well, you've got to think about it. All of your load circuits are going to be protected either by a breaker or a fuse disconnect system. Okay. So let's say that the breaker protecting one of your branches is a 10 amp breaker. Okay. So in both the 3-phase UPS is a 10 amp breaker, and in the single phase UPS it's a 10 amp breaker. Well, let's go to a trip curve. Now, this is just a standard trip curve of a breaker. I can't even remember which model it was. But if it's a 10 amp breaker, we're saying we can only get 28 amps, which is 2.8 times the nominal rated current of that breaker. And if we follow that up, my terrible drawing, it's going to take 4 seconds for that breaker to trip on a 3-phase UPS. And if you have a short circuit on that load, that short circuit is probably going to pull down the inverter voltage, maybe to a level that is not suitable for your load circuits. Yes, you will transfer to bypass, but it's going to take anywhere between 0 and 4 seconds to do that. But with the 120 volt UPS, you have 3.5 times Actually, tell if it's a 10 amp breaker, you can have 83 amps, but let's say the UPS is loaded at half the load. So you only have 40 amps available. That's still 4 times the 10 amp rating of the breaker, and therefore the breaker is going to trip in 0.01 seconds, near enough instantaneous. So you can see how important it is. Well, not how important, but how much better a single phase UPS clears faults on the output of the system. In most scenarios that I have found, every time we replace a UPS with a 208 UPS, it's because the original UPS was a 208 volt UPS, and there's a 208 volt distribution panel on the wall, and you don't want to go through the process of changing that panel to a 120 volt single phase panel. And I understand it, but I just wanted to make it clear why a single phase UPS is usually always better than a 3-phase UPS. The next misconception is a 10 kVA UPS will give you 10 kilowatts of power, and that is not correct. Most UPSs are rated at 0.8 power factor. You can buy a UPS designed for unity power factor, but a standard UPS is rated at 0.8 power factor. That means a 10 kVA UPS will only give 8 kilowatts of real power. So if you connect a purely resistive load to a 10 kVA UPS, you will only be able to load that UPS up to 8 kilowatts before a current limit situation arises. And that's because the power factor for that resistive load is unity, okay? And you've got to understand as well that most loads connected to a UPS system have inductance, capacitance, and resistance. So it's usually, the industry standard is 0.8, although that is kind of changing now because we have power factor corrected power supplies, and the power factor is getting closer to unity on some of these power supplies. But historically, 0.8 power factor is what is required for a UPS. Next misconception, we lost power to the input of the UPS. Why didn't we switch to bypass? Now, this is such a common question because a lot of people say, well, if we have bypass, switch to bypass, because therefore we're not cycling our batteries, we're protecting the batteries. But you've got to remember, the AC, if you lose power to the AC input to the UPS, it's nearly always fed by the same main HV bus back at the MCC. And now, if the MCC that feeds the AC input has tripped, then usually the plant will be going through an unstable situation. If power, because you've got to remember, if that MCC that feeds the AC input has tripped, there are many other things related to that MCC that are going to have a domino effect in the plant. So that may mean that the bypass, if you switch to bypass, which is fed from somewhere else in the plant, but using the same HV power supply, there may be large pumps stopping and starting and things going all over the place that can cause voltage dips onto the bypass. So if we transfer to bypass, those dips would be seen by the load circuits, and it could mean that the load circuits would operate erratically. If we stay on inverter and have the batteries provide power through the inverter, then it doesn't matter what the bypass is doing. The inverter is going to be perfect, 120 volts, 60 hertz going to your load circuits. It does not matter what the bypass or what's going on in the plant. It will be rock solid, 120 volts, 60 hertz, and your load circuits will be protected. That is why we do not switch to bypass, even though it is available if we lose AC power into the UPS. And here's an example, a good schematic of what that means. You can see at the top here, that's the main HV bus, and you can see that it's been tapped off here. MCC2 is where the bypass is fed from. MCC1 is the MCC that's failed, but remember, we've got MCC3 connected to this HV bus as well. And that has loads of three-phase motors connected to it. So if MCC1 fails, which causes a domino effect on some of the plant, and a control signal gets sent to these motors to say, oh, there's something going on, you need to turn this pump off, then turning on pumps and turning off pumps is going to cause disruption on this bypass supply. And we don't want that to be seen by the load circuits. So the inverter is going to be perfectly nice, beautiful sine wave, while all of this messy stuff is going on in your plant MCC. The next one, the battery breaker on my UPS tripped. Do I have a bad battery? Maybe. It could be that you have a bad battery, but in most situations, it might not be, because remember what I said earlier about UPS manufacturers protecting the battery? Well, battery manufacturers specify the rating of a battery to a specific end voltage, and the industry standard for industrial UPSs is 1.75 volts per cell. So an example here is for an Enesis 3CC9 battery, it will give you 200 ampere hours at the C8 rating. And what that means is you'll get 200 amps total for 8 hours. 25 amps basically per hour for 8 hours. And then at the end of those 8 hours, our expectation is the battery will be around about 1.7 volts per cell. So let's get that out of the way. The next thing is the battery manufacturers recommend that a lead acid cell should not be discharged past 1.6 volts because that can lead to damage that cannot be reversed. Okay, so there's a buffer there. We say 1.75 volts is the best voltage to go down to, but there is a little bit of leeway. They could go down to 1.6 volts and they'll still be okay. Go below 1.6 volts and all bets are off. So the only way to protect the battery from over discharge is for the UPS to prevent the battery going below this voltage. So an AMETEK SCI UPS will trip the battery input breaker and transfer the system to bypass when the system gets down to 1.75 volts times the number of cells. So if you walk up to a system, especially if you've had a power outage recently in your plant and you find that the battery breaker is in the tripped position, it's probably because the battery's reached their end voltage, and all you need to do is reset the breaker and the charger will charge the batteries back up again. We had a fault on a load circuit and the UPS transferred to bypass. Why did it do that? Okay. I'm going to try and take this a little bit slowly. Inverters have devices inside of them that must be protected from overcurrent situations. And the power switch of choice in nearly all UPSs these days is an Igbt, which is an insulated gate bipolar transistor. Okay. The thing about IGBTs are they are very sensitive to overcurrent situations. So for a 10 kVA UPS, we've already mentioned before on a single phase system, the output current rating is 83 amps. So at a certain point, let's say you have a fault somewhere on your load circuit. If that fault current goes above 83 amps, the system will go into current limit to protect the IGBTs, okay? Because the system designer, in truth, we use oversized IGBTs, so you are going to have some protection, but let's say the designer put 100 amp IGBTs in there. What we're saying is if the load fault asks for more than 83 amps and it goes above 100 amps, those IGBTs could fail catastrophically because you can't protect an IGBT with a fuse. The current, when they see high current, they detonate pretty much instantaneously. There is no fuse quick enough to protect an IGBT. Okay, so we have to do the current limiting electronically. So current limit is simply, and there's a lot of confusion around current limit. It's simply reducing the voltage of a system to maintain current at a certain level. So hopefully this example will give you a better idea of how current limit works. Let's say the load, well, using Ohm's law, if the output load is 83 amps, that means the total overall resistance of all of the loads put together is 1.44 ohms. And you can see the calculation I did there. R is equal to V divided by I. Voltage is 120 amps divided by 120 volts, sorry, divided by 83 amps. So at that moment in time, when the load current is 83 amps, that means the load, all of the loads added together is 1.44 ohms. So if the load increases, that means the resistance decreases, because they're not, what's the word I'm looking for? They're, if the load goes up, then the resistance goes down. And let's say the resistance goes down to 1 ohm, then the current asked by the load is going to be now I is equal to V over R, which is 120 volts divided by 1 ohm, which is 120 amps. That's too high, especially if we were using 100 amp IGBTs in the system. Those IGBTs would blow up. So the only way to reduce current is to lower the voltage, because the resistance of the load is the resistance of the load. We can't change that, okay? The only way we can lower the current is by lowering the voltage of the system. So let's, to stay at 83 amps, we would have to lower the voltage. So V equals IR once again. So it's 83 times 1, which is 83 volts. So that means we would have to lower the output of the UPS to 83 volts to keep the load at 83 amps. And that's too low. Sorry, that's too low for your load systems. So what the UPS is going to do is it's going to transfer to bypass. Okay, when it sees the voltage of the inverter going down too low, and it's doing that to protect its IGBTs, then the system's going to say, okay, voltage is too low, let's transfer to bypass. The bypass is a much more robust, solid supply of power, and it can do whatever it needs to do to clear that fault on the output. And then you will have to go back to the UPS and transfer the system back to inverter once you've got rid of that load problem. Hopefully that explained current limit and didn't confuse you more than necessary. And there's just a diagram of what's happening. So if we're saying that 120 amps is too much to go through our inverter bridge, which is where the IGBTs are, then we transfer to bypass. It will clear the fault. And then once that fault is cleared and taken care of, you can put the system back onto inverter operation. Okay. And the next misconception is all the PCBs should be plug and play. And we truly wish that they could be. But unfortunately, there are some circumstances that are out with our control, which, especially in this day and age, which means they can't be. So on a digital system, all PCBs have analog to digital converters on them. And we must use resistors to drop the high voltage sensing of any analog value to the analog to digital converter. So our battery is 135 volts DC. We have to use resistors to drop that voltage down to a suitable level, anywhere between 5 and 12 volts, to go into the analog to digital converter or digital to analog converter. Those resistors have tolerances, and therefore we cannot guarantee the actual resistor value when manufactured. And that means that the PCB has to be calibrated to the system that it is installed in. Okay? That's the only way that you can calibrate an analog to digital converter, is to put it in the system and to measure the voltages and then tell the system what those voltages are because of those resistors. And there's also some of the solid state devices, whether it's a processor or an op amp, they have tolerances as well. So if the board is replaced, that board will need to be calibrated in most cases. And calibration is a function that is protected in our menu system on an AMETEK solid-state control UPS to prevent a situation that could cause UPS to fail or be damaged if miscalibrated. We have to protect that menu system, because if we allow people to go in there and mess around with it, it's not clear in most circumstances what you're messing around with, and you could do something that could damage the UPS. So that is why it is password protected. And then on top of all of that, we also have continuing R&D software development, and we have to take care of obsolescence. And especially in this day and age, the processes that we use inside our UPS go obsolete nearly on a yearly basis. And sometimes it's not a like for like replacement on some of those processes. So R&D have to come up with ways to deal with the obsolescence. And that means going to a different chip on some boards, and therefore they're not quite as backwards compatible as they could be. And we have to go in using our proprietary software and make some changes. So there are some boards that, yeah, you probably could get away with plug and play, but for the majority of our boards, especially the inverter control board, the charger control board, and the static switch control board that is actually monitoring AC and DC values, they're probably going to need to be calibrated. The main control board, the display, yeah, it is pretty much plug and play these days, but all the other boards related to it, unfortunately, are not plug and play. I told you I'd run over 6 minutes already. Oh boy, I think this is the last misconception. I can move the manual bypass switch to the bypass position without following a procedure. Please do not do this. The bypass switch is a make before break switch, and that means it intentionally parallels the output of the UPS to the bypass supply for a short duration while the switch is moving positions. If the output from the UPS is on inverter, then there can be a situation where the inverter output and the bypass may not be in sync, and that could be instantaneous. So if the bypass is out of tolerance frequency-wise, or if there are large non-UPS related loads in the plant causing the bypass to be unstable, the phase difference could cause a voltage difference between the two sources, and that would lead to high circulating current. And that could lead to either the IGBTs blowing up, or it could even trip the incoming bypass breaker because there's too much current. And excuse me, if you've just moved the bypass switch from normal to bypass, and in doing so, you trip the incoming bypass breaker, well, you can guess what happens there. The bypass breaker trips and you go to bypass, you've dropped the load. So do not move the bypass switch to the bypass to load position while the inverter to load static switch is on. And this next slide should help you see that, okay? So remember, this red line here, this is in normal operation. The inverter is feeding the load, okay? Now let's say this is our bypass supply coming in here, and something has caused the synchronization between the inverter and the bypass to go out of whack for some reason, okay? Let's say they're completely out of phase with each other. So let's follow this hashed line here. At the top here, the bypass is at the top of its peak on the voltage, but at the bottom here, the inverter is on the bottom of the peak of the voltage. Now, if you use calculation, the peak of the waveform is 170 volts. So up here, you've got plus 170 volts. Down here, you've got minus 170 volts. So across this contact here that you are about to close in when you go to bypass to load, you are going to have a difference of 340 volts, okay? And what's going to happen usually is, because the bypass is more robust source, it's going to feed into that difference, and it will try and feed back into the inverter IGBTs. So either the inverter IGBTs will blow, or the breaker that feeds the bypass source at the MCC, sorry, is going to trip. And if you just went to bypass, you're going to drop the load. So always follow the procedure. There's protections in place to make sure that you never do that. Oh, goodness me, I've still got another question. I have a paralleled UPS. When I switch to bypass on UPS A, it shows that the static switch is open on UPS A. Why didn't it switch to bypass? As we've discussed before, it's never good to have two voltage sources parallel together if you cannot control both sources. When you have two inverters connected in parallel, there's electronics that speak to each other, and we can control those two sources, and they are always perfectly in sync. But when you press one of the UPSs to transfer to bypass, if we allowed it to do that, then you would have one system on bypass, one system on inverter, and if the bypass, which we have no control over, changes or goes out of tolerance, then you are going to have a situation where you're going to have circulating current again, pretty much identical to that situation that we had before. So our system, our parallel systems are clever enough, intelligent enough to know that. So what we do is, instead of turning UPS A static switch to bypass to load, what we'll do is we'll switch off the static switches on UPS A and allow UPS B to feed all of the load circuits. I think, do I have a drawing? Yeah. So you can see here that these static switches, this is UPS A, they're both off because somebody pressed bypass to load on that system. But UPS B, it carries on feeding the load circuits regardless. Okay. Oh. More questions. If I'm on bypass, I still have battery backup, right? Absolutely not. Another really big misconception. Once you are in either static bypass, in other words, on bypass through the static switch, or you are on maintenance bypass, you are not supplying the load from the inverter. And if the inverter is out of the game, then you do not have battery backup. Simple as that. Okay? You only have battery backup when you are on inverter. So that is a very big misconception. And basically there's a picture showing you it, okay? If you are on bypass, that means that static switch is off, and therefore you have no way of getting the battery power through the inverter and out through the static switch. If the UPS says it's in bypass, but the manual switch is in normal, what's going on? Well, that's usually one of two things. Either A, someone has pressed the bypass to load push button on the UPS, which has transferred the system to static bypass. Nothing to do with the maintenance bypass switch. Remember, that's a rotary handle. It's just a push button to transfer the system to static bypass. Or it could be that you had an overload on the output of the system and it transferred to static bypass automatically. And the maintenance or manual bypass switch, which is the physical switch, is not affected by the position of the static switch. They can be two completely different positions. So if the manual bypass switch is in the normal position, then the static switch can be in the bypass position. The two are not related. So in this situation, the first thing that you should always try and do is press the inverter to load push button. Our system is clever enough for you to know, clever enough to know if there is still a fault present. So it won't go back to inverter if it thinks it will jeopardize the load circuit. So if you walk up to a system and the maintenance bypass switch or the manual bypass switch is in the normal position, but the static switch says it's in bypass, try and press the inverter to load button and see if it goes back to inverter. And there's just a drawing confirming that, okay? Power in static bypass, this static bypass switch is on, so power is flowing all the way through here, but the RMBS, which is this section here, these are in the normal position, okay? So the static switch is on bypass, but the RMBS is in normal. So the two are not exclusive. Woohoo! Only 14 minutes over. Sorry, guys. I really just, guys and girls. So I do apologize for going over. So now I can get through the questions. So please ask questions if you have any. So let me go through the list. Will PDH or CEU certificates be sent for this webinar? The answer to that question is not at present. Not at present. We do not offer PDHs or CEUs. It's something we are looking into. If the batteries are depleted and the UPS is operating in bypass mode, are the batteries still being charged? That depends if the AC input to the UPS has come back on. If the AC input to the UPS has come back on, then yes, the batteries will be recharged. It's on an AMETEK solid-state controls UPS. There is no, as long as the AC input breaker to the UPS is closed, then if it sees power, it will recharge the batteries. Obviously, you need the AC input to be on, and you need the battery disconnect to be closed. Somebody's asked, could you explain current limit for a battery? It's exactly identical to the current limit that I mentioned for a UPS. It's just done on the DC. Current limit is just, all we do is we lower the voltage of the charger to keep the current at an acceptable level. And that's all down to the resistance of the batteries. If you've had a battery discharge, the resistance of the batteries goes down, which means they will accept more current. And therefore, when the charger comes back on, it will lower its voltage to maintain a suitable current to those batteries. That's, everybody thinks that current limit, somehow we have this magic thing that changes the current without changing the voltage, but it's Ohm's law. The only way we can reduce the current on either the charger or the inverter is by reducing the voltage. Hopefully that explains that. And somebody has asked, how do we tune the calibration? Basically, for our systems, we go into a password protected menu and we use a calibrated fluke meter and amp clamp to monitor the voltages of the inputs and the outputs. And then we tell the system what those measured voltages are compared to its digital value, and it does its calculation and calibrates the system to those new voltages. Okay, I don't see any other questions coming in. Oh, there are a couple of others. How much harmonics does a UPS generate? You would have to go to the data sheet to see that. It's listed as a total harmonic distortion, and I don't have the details. And all of our UPSs have different values. Our DPP is different to our ferroresonant system. But on a pulse width modulated system, it's a relatively small amount of distortion. But I couldn't comment on what that actually is. But I could pass that on to our engineering department and get back to you. How do you calculate the incident energy produced by the UPS so the distribution panel can be properly labeled? That's a very good question. And it's out with my skill set. Usually you would have a software package that you could tell them what the rated power capacity of the system that is supplying a distribution board is, and then it calculates the incident energy for you. I'm not an incident energy engineer, so I cannot answer that question specifically. But once again, I can pass that question on to our engineering department, who may be able to help you. For battery replacement, I believe I've always been told to place the UPS in static bypass before opening the DC breaker for isolation. Then only going back to inverter after introducing the battery back into the system. Why is the static bypass necessary? Seems like we are eliminating 2 to 3 layers of redundancy from the duration of the job if a temp battery is not utilized. That is an excellent question. Now, in most cases, you can open the battery input breaker on an AMETEK Solidstate controls UPS, okay, on a UPS. And a UPS has a charger, an inverter, and a static switch inside it. If you are working on a standalone inverter that is being supplied by, let's say, a station battery and a station battery charger, then if you open the DC input breaker to an inverter, then it will, on our older systems, it will trip the system to bypass automatically. So I can understand why you're told to go to static bypass, because therefore it prevents any of that from happening automatically within the UPS. But in my experience, especially if you have a newer microprocessor controlled UPS supplied by AMETEK Solid-State Controls, you should be able to quite easily open the battery disconnect, replace the battery, and then close the battery disconnect in once the battery replacement has been performed. The other question that leads into is, you know, a lot of people say put the system in bypass and charge the batteries first before you put the batteries in operation on the inverter. And 99 times out of 100, that's not necessary, because the battery will come, the new battery will come with a relatively good charge from the factory usually. So when you close the battery input breaker in, as long as the overall string is above that 105 volts for a 60 cell system, then the charger is going to go into current limit and do whatever it needs to do to charge those batteries correctly. Because the way that the UPS sees it is, it's just like if it had an AC input failure. If you went onto battery operation, discharge the batteries all the way down to, let's say, 106 volts, and then the power comes back on again, nobody goes in and transfers the UPS to bypass and allows the batteries to charge back up again before the inverter comes on. No, what happens is, if it's before that, if it gets down to 106 volts and the power comes back on again, then the charger just comes on and starts charging the batteries and supplies power to the inverter. So if you have any questions regarding that, just let me know. Contact us before you do any of the switching. Just give us the serial number of the UPS and we'll be able to tell you quite easily whether you can open that DC input breaker and replace your batteries without any issues. I have no problem with doing it. I used to do it all the time. Like you said, it removes layers of redundancy and you don't need a temp battery and all that kind of stuff. But you do have to remember you're on bypass. Even though you're on inverter, if you have a power failure when you have the battery disconnected, you will transfer to bypass as long as bypass is available. Hopefully that explained that. Okay, we've got some more questions. Can the MBS or RMBS switch line and neutral? Oh, that's a very good question. I think we do supply switches that can do that. I just can't imagine why you would want to. I can't think of it. But I'm pretty sure if you want something like that, we can supply it. That is all the questions that I have. So hopefully I have explained or answered your questions correctly. I do appreciate everybody geez, an hour and a half nearly. Goodness me, I'm going to have to do better next time and try and keep it within the hour. Taylor's just posted in the comment section there, the recording of this presentation will be available at our YouTube channel tomorrow. And there's the link for it. And also, if you have any questions or concerns, there is the contact details for us. You can go to our website and use our contact us. You can email us at the email address sci.marketing@AMETEK, or you can give us a call. And goodness me, a human will answer it. And we will speak to you about it. So we have one more question. We have had issues with our battery charger input fuses blowing when closing our DC breaker from the battery to inverter input. What could cause that? Well, that's a good question, Paul. What I would say is give the 1-800 number a call. You'll get routed to the specific technical manager for your region, and he could help you out with that more, because that doesn't sound right. We have had issues with our battery charger input fuses. If you're talking about if it's not the battery charger input fuses, but it's the inverter input fuse, then it's usually because it's the procedure is not being followed correctly. Whether you have a pre-charge switch or whether you're supposed to start the charger first and then close the DC input breaker. It can be caused by inrush into the DC capacitors if it is the fuse that feeds the inverter bridge. But if it's the fuses that feed into your battery charger, that doesn't make sense and it should not be happening. Okay. I'm definitely going to get off this call before an hour and a half is up. I've taken up way too much of your time. Keep an eye out for emails for the next webinar. It will be usually the third week of the month. And if you have any suggestions for what you want the topic to be on that webinar, please don't hesitate to get in contact with me. I really like to hear what you want me to discuss. And I usually try and integrate it within a month or two into a new webinar. So you will get a survey. Please fill it out. And if you have any suggestions on what you want me to discuss, then I will definitely take that on. So once again, enjoy the rest of your Wednesday, wherever you are in the world. Thank you for taking time out of your day to listen to me ramble on about UPSs, and take care until next time. It was a pleasure speaking with you. Thanks very much.